So far we've talked about how to represent a complex number as a point in this strange plane, imaginary direction, real world, and then as we can write the complex number z as x plus iy. X is the component in the real world, y is the component on the imaginary axis. And then we talked about I has the interpretation of being square root of -1, an imaginary number. So now that we have those, we can start doing just algebra with complex numbers. So let's try multiplying complex numbers. And this goes through just exactly as you would expect. The only thing you have to remember is that I squared is -1. So for example, very straightforward example, let's take 3 plus 2i, it's a complex number, times 4 minus 5i. And you multiply it out just like you normally would. So there it is. And then I just have to remember that I squared is -1. So I'll group the terms that don't have the I, and I'll group the terms that have the I, just like I'm grouping components. So I'm going to have 12 plus 8 minus 15 is -7, plus 10 because I squared is -1, and so I get 22 minus 7i. So that's how I would write that. If you're going to do it in general, maybe you have, z1 is equal to x1 plus I y1, and then you have z2 is x2 minus plus I y2, and then you're multiplying those two numbers together. Z1 times Z2 is going to work exactly the same way, so we can just write it out in general. So there it is, in general for any two complex numbers. Notice the minus sign here, so the minus y1 times y2, that minus sign came from multiplying these two terms together with I squared is equal to -1. Now that we know how to multiply complex numbers, I'm going to do one more operation. So it's called complex conjugation. So every complex number has what's called a complex conjugate. And that is called Z star. So the star means complex conjugation. And to find it, you take Z and you change all i's into minus i's. So everywhere you find an I, you change it to minus I. So as a simple concept test here, suppose I've got a number z, which is represented by this point in the complex plane. Which of these points represents the complex conjugate z star, a, b, c, d, or e? So this will be something that you can use to check yourself, so I won't be going over the answer to this question, but make sure you can understand, based on the definition of the complex conjugate, changing all i's to minus i's, can you answer which one of those is the right answer? So we have the complex number z, x plus iy, and we have its complex conjugate z star is x minus iy. So note something useful. Let's take z times z star. What do we get? X plus iy times x minus iy. Hopefully you can do this in your head without having to multiply it out. Remember that a plus b times a minus b is a squared minus b squared. Something really useful to remember. So in this case, it's x squared is a is x, so the first term is x squared, minus b squared, which is iy squared, which is x squared minus I squared times y squared. But minus I squared is minus 1. Sorry, I squared is minus 1, so minus I squared is plus 1, so that's x squared plus y squared. Notice that this is a real number. X and y are real numbers, right? And so the i's have gone away. So if I ever need to get a real number from a complex number, z, if I multiply by the complex conjugate, I get a real number, and it's equal to the x squared plus y squared. So this can be useful, and I'll show you how. We're going to do an example here. So let's do this example. What is the real part of this complex number? So I've got a complex number there, 2 plus 3i divided by 4 minus I. What's the real part of that? Here's the wrong way to do it. So I'm showing you because people do this and I want you to not do this. The wrong way is to say, oh, I'll just ignore all the i's. And that would be 2 over 4 is equal to 1/2. So this is wrong, so don't do this. You can't just ignore the i's, okay? So here's the right way to do it. The right way to do it, plan, is to write, I have to write z in the form x plus iy. So it has to be something which is a real number plus I times something else. And then the real part is x. So this is the real part of z. And this is the imaginary. Y is the imaginary part. In order to do that, the problem is I've got a complex number in the denominator. But what I can do, because I know that if I multiply a complex number by its complex conjugate, I'll get a real number. So I want that denominator to be real. So to do that, I'm going to multiply the top and the bottom by the complex conjugate of the denominator, and you'll see what happens. Z is 2 plus 3i divided by 4 minus I. And I'm going to multiply the top and the bottom by the complex conjugate, 4 plus I over 4 minus I of the denominator. Sorry, 4 plus I over 4 plus I. I didn't do anything. I multiplied by 1. So I changed nothing. So now I've got 2 plus 3i, 4 plus I on the top. And on the bottom, I've got a number times its complex conjugate, which is going to be 4 squared plus 1 squared, which is which is 17. So 2 plus 3i times 4 plus I divided by 17. Okay, I have to do the multiplication on the top, so let me do that. So there it is, and let me just simplify it. I get 5 over 17 plus 14 over 17 times I. And so what's the real part of z? Is 5 over 17. So that would be the answer to that question. So if you're looking for just the real part or the imaginary part, so I'm looking here for the real part, I need to write it in the form of x plus iy. The real part is the x, and the imaginary part is whatever is in front of the I. Okay, so now you have some experience if you have z equals x plus iy with the complex conjugate z equals x minus iy, and z star is a real number, which is x squared plus y squared. And just some notation, usually this is written like this. And this there's several ways that you call this. I might usually say the modulus of z. You might hear mathematicians say the argument of z. which I don't usually say that, but if you see it in a book, that's what it means. And then I might also say the magnitude of z, because it reminds you of a vector, right? The magnitude of a vector is the sum of the components squared. So this is a lot like the magnitude of the vector x squared plus y squared, like the sum of the components squared. Okay, so now with that in mind, I want to go a little bit further and start talking about polar notation and making further connections between complex numbers and vectors. So just a reminder, let's think about the comparison between vectors and complex numbers. So you know you can describe a vector. Let's look over here at this vector a, which I drew. You can describe it in terms of its components, ax and ay. Or, equivalently, you can describe it in terms of a magnitude and a direction. So the direction is given by theta, and the magnitude is given by the length of this side, which is a. And you all know the relationship between those two. Let me just write those down quickly. So you can get the components if you know the magnitude and the direction using these formulas here. And if you know the magnitude and the direction, if you know the components, you can get the magnitude and the direction using these formulas over here. Okay. So that's just a review of basic vector algebra. And I would call it polar notation. So if you're giving the magnitude and the direction, you're giving a radius and an angle, and that's polar coordinates. The same thing is true for our complex number z, so which you can see on this diagram at the right. Looks exactly the same. I can describe it with quote-unquote components. Though they're not really components, but they're kind of pieces of it. I can describe it as a real part of z and an imaginary part of z, which we call x, and this is what we call y. So that's how we've been describing it before, x plus I, y. I'm giving the real part and the imaginary part. But I could also give you a quote-unquote magnitude and a direction. Right? So the direction here, let's call it theta, and the magnitude is the length of this side, which is z, or the modulus. So we know how to calculate the magnitude, which is up here, exactly the same. And then this direction is sometimes called the phase. So we have modulus, and the angle is called the phase. So, or like a magnitude and direction of a complex number. So any complex number you can represent in the form shown above, like x plus I, y, real part plus I times an imaginary part, or you can represent it with a magnitude and a phase, and we want to talk about what that looks like. Before I go any further, let me just write down the analogous formulas here, which look exactly like you would expect. So just exactly the same as for the vector. Just instead of the component ax and ay, I'm using x and y, the real part of z, and the imaginary part of z. Okay, so let's do an example. So here's an example you can use to check your understanding. I'm giving you a complex number here. Z is minus 1 minus I, and I want to know the magnitude and the phase of this number. So those are your choices, and I'm going to give you a hint. And this is a really important hint, and some practice you should always put in place, is draw a picture. That'll help you catch errors and let you check whether your answer makes sense or not. So go ahead, pause the video, see if you can decide on one of these choices, and then we'll work it out when we come back. Okay, so hopefully you have chosen one of those answers, and before we start, let's draw the picture. So this is the complex plane Z. This is the real part of Z here. And this is the imaginary axis. Let's put here 1, 2, 1, 2, 1, 2, 1, 2. So this number has a real part of minus 1 and an imaginary part of minus 1. So it's down here. Okay. So now I want to know the magnitude, which is basically this length, or the modulus, which is this length, and I want to know the phase, which is this angle measured from counterclockwise from the positive real axis. So this is theta. Okay, so because I know that this distance here is 1 and this distance is 1, this angle must be 45 degrees, and so the magnitude z must be equal to the square root of 2, which eliminates these choices. And then just by looking at the picture, theta must be equal to 180 degrees, so that takes me over to the minus real axis, and then another 45 degrees downwards. So that's 225 degrees. If you convert that to radians, that's pi plus pi over 4, which is 5 pi over 4. So this is the right answer here. Choice A. That's what I got from drawing the picture and thinking about it. Now, what if you tried to actually work it out? What would you get? Remember, I have x is equal to minus 1, y is equal to minus 1. So I would get the magnitude of z is the square root of x squared plus y squared, which is the square root of 1 plus 1 squared, which is equal to square root of 2. So that agrees. And then what if I did this? Tangent theta is the imaginary part of z over the real part of z. That would be tangent theta would be equal to minus 1 divided by minus 1, which is 1. So theta would be equal to the inverse tangent of 1. And if you plug this in your calculator, your calculator will probably, unless you have a very smart calculator, will probably give you 45 degrees, which is pi over 4. And this should puzzle you, because the picture, we found that theta was 5 pi over 4. So what happened? When you take an inverse trig function, you get two solutions. There's two solutions to this. One of them is pi over 4, and the other one is 5 pi over 4. Both of those, so if I take the tangent of pi over 4, I get 1, and if I take the tangent of 5 pi over 4, I get 1. So both of those are solutions. How do you know which one to choose? You have to draw the picture. So from the picture, I know that this is the right one to use. And that's why I'm telling you, you have to draw the picture and you have to think about it. If you just trust your calculator blindly, you would end up with pi over 4 and you get the wrong answer. So always, always, always draw a picture, especially when you're dealing with inverse trig functions. You have to think about which solution do I need, the one in the first quadrant in this case, or the one in the fourth quadrant, or sorry, the third quadrant. And of course, from the picture, it's clear it has to be the one in the third quadrant. So that's really, really tricky. Okay, so going forward, we want to be able to, we know the magnitude and the phase of this complex number, and what I want to do in the next set of slides is I want to be able to write z in terms of theta and the magnitude. So I want to be able to write this mathematically using the magnitude and the phase. So that's what we'll get to next.